morning to all. Today we are going to see about the pericyclic reaction, concerted reactions. So what are pericyclic reactions? Why are they so called? Insensitive to presence of polar solvents and catalyst. This is do not involve ionic or free radical intermediates, and the following concerted mechanism involve the simultaneous breaking and making of bond proceeding through the cyclic transition state, and they are so called because they takes place through the cyclic transition state following the concerted mechanism. The characteristics of pericyclic reactions: they are initiated by heat thermolysis or light photolysis. Highly stereospecific thermal and photochemical reactions yield the product with different stereochemistry. Conservation of orbital symmetry. For example, free calciferol on heating gives cis isomer, but on irradiations its form transition product is 9H and 10CH3 or the transition. The concerted reaction is, there are the three types. One is the electrocyclic reactions, cycloadhesion reactions, sigmatrophic rearrangement. There are the three types of concerted reactions. So first we are going to see about the electrocyclic reactions. So here the ring closures or conjugated systems. This is for the electrocyclic reaction is a pericyclic reactions, where their net result is one bond is being converted into one sigma bond. This is for the electrocyclic reactions are photo induced or the thermal. The photo are induced or thermal. So this is for the electrocyclic reaction. You see the heterotrienes to reactions of the bi-bonds. It is electrocyclic reactions is a cyclohexadiene will be formed. So here is formed as a transition state, then will be a reactions follow, right? Then next, the cycloadhesion reaction. What is cycloadhesion reactions? So this is involve the formation of a cyclic product due to the addition of two different bi-bonds. Additions of two different bi-bonds containing components which are joined by the newly formed two sigma bonds. Here for the two bi-bonds it is formed as a two sigma bond, and there are end at the expense of the two bi-bonds. So here two bi-bonds and its formation of two sigma bonds is formed here. Same like this reaction is also formed for bi-bonds and two bi-bonds. It's formed as like this. So this is for the cycloadhesion reactions. Next, the sigmatrophic rearrangement. What is sigmatrophic rearrangement? There are the concerted unimolecular isomerization reactions characterized by the overall movement of sigma bond from one position to another with and accompanying rearrangements of pi electrons of conjugated system so as the recommended the new sigma bonds. Example for 3,3 Hope reaction, 3,3 reactions for sigma bond undergoing to movement of the showing for red thick line. So this is for the formation of reactions. So sigmatrophic reactions for a unimolecular isomerization reaction characterized by the overall movement of sigma bond. So this is for the sigma bond from one position to another is accompanied of the reaction. Here is the one position to another position. So this is the new position of the sigma bond. So this is for the sigmatrophic reactions. Here methods of analyzing pericyclic reactions: molecular orbital correlations diagram methods and FMO methods and PMOS methods. So Woodward-Hoffman rules. What are the indicate this rule? Predict the allowedness and otherwise of pericyclic reactions under the thermal and photochemical conditions using above the methods. Therefore, the basic understanding of molecular orbital of conjugated polyenes systems and their symmetry, the properties is essentially to apply the above the methods. So this is for the methods of analysis of pericyclic reaction. So the structures you see the symmetry of the properties of molecules orbitals. Here the 4p atomic orbital interacted to give the 4p molecular orbital 1,3 butadienes 1,3 butadienes. Energy of the p atomic orbitals. Here you see the by bonds p orbitals. Here you see the nodal. You saw the lower unoccupied molecular, and here see the higher unoccupied molecular. So see the molecular orbital is the ground state energy and excited state energy level. You see the 4p atomic orbitals interact with the go to 4p molecular orbital 1,3 butadiene. So this is for properties of the molecular orbital. Here the energy and the molecular orbital descriptions of 1,3,5 hexatrienes. One of the another example for here the ground state energy and excited state energy of molecular orbital. So you see here the diagram is so the green color and opposites, and here this opposites splitting of the ground state to excited state. Here also is psi 1, psi 2, psi 3 and psi 4, psi 5 and psi 6. It is ground state to excited state. The molecule will be changed as a molecular orbital description, right? Then next the symmetry properties of pi molecular orbitals of 1,3 butadienes. Here see psi 1, psi 2, psi 3, psi 4, the ground state to excited state. The butadiene, here the anti and syn position, right? Here is also S and A, another is psi 3 is A and S, and psi 4 is S and C. This is symmetry formation. C2 and sigma is the property. VRC generally we call it as a butadiene, for example of the symmetry properties of 5 molecular orbital 1,3 butadiene. So molecular orbital of 1,3,5 hexatriene. Another one example for 0 to 5 nodes. Here the psi 1 to psi 6. Here the molecule is ground state to high occupied molecular orbital to low occupied molecular. Here the different arrangement 0 nodes. Here is there is syn and anti. The position is opposites like this, right? So this is for the another one example molecular orbital system of 1,3,5 hexatriene, right? Then electrocyclic reactions of ring closure of conjugation. Some examples here I am going to discuss about. The electrocyclic reaction is pericyclic reactions where the net result is 1 by bond. Here is 1 by bond being the converted into another sigma bond, the cyclobutane. The same as the cyclotriene is here is the double bond is converted as a cyclohexadiene. This is a sigma bond, and octatrienes is called as a cyclotrienes. Cyclo reactions of photo induced or thermal reactions. Electrolytic reactions. What is the electrolytic reactions? Here the image is very clearly said that there is one ring closures of disrotatory formation. Here the p orbital is rotating and like this and rotating like this. It is arranged this ring closer disrotator like this, right? Another one is the conrotator ring is totally the molecule is oppositely ring closures, right? So see here the blue colors of orbit, and it is a green color of orbit. It is oppositely joined, right? Then it is an electrolytic. Another one is C2 axis of the symmetry, the conrotatory connections and disrotatory connections of one example C2 axis. Here the molecule of one nodes of Mobius, the connectivity of this condisrotatory and this to this and this to this, and disrotatory is the same side of the connectivity. Here is disrotatory and disrotatory. The mirror image, a mirror symmetry of this no nodes of the Huckel reaction. So this is one nodes of the Mobius and another one nodes of the nodes of the Hercules, right? Then electrocyclic disrotated ring opening of cyclic butene to 1,3 butadiene. Here you see the formation of butene and rotatory and sigma symmetry maintenance of here the formation of breaking of these bonds, right? Here the cyclobutane and butadiene, the psi1, psi2, psi3 and psi4, and is a formation of the S and AA as sigma to pi and sigma to sigma star and pi to pi star. Here is the arrangements of the butadiene SA. So another example for cycloaddition conrotatory of the ring opening of the same compound butadiene 1,3 butadiene. Here is opposites. Here like this sigma pi and pi star to sigma, and then here is SA and SA, and then psi1, psi2, psi3. Here is AS and AS. Here is just opposite of this reaction. So another one is the Fourier orbital methods for the electrocyclic reaction. Here you see the rotatory, the pi 2 homo of butadiene, the rotation of the conrotatory like this. This is for rotator here and rotate here, the bonding interaction like this, and then its bonding orbital also like this. The molecule is of H2 homo of butadiene disrotatory. It's an anti-bonding interaction of this transition state, and this anti-bonding of the orbital is found. So this is for the frontier orbital methods for the electrocyclic reactions. Another only one symmetry of the HOMO is an important determining of the course of the reaction, which is called as a HOMO is a symmetric disrotated ring closes. Here see the rotation is blue color is close together, and is green is outside. Another one point, you see the HOMO is asymmetric compound like this. It is just like that, is a conrotated ring closures of like this, right? And then disrotatory is disrotatory is pi 3 homo hexotriene. The like this the bonding formation of interaction transition state, and then is bonding orbital will be formed, and then H3 is the homo of hexotriene. The anti-bonding interaction of the transition state anti-bonding orbital will be formed. Yeah, an electrocyclic reaction is completely stereospecific reactions. Here you see the 2E and 4Z and 6E octatriene. This is for the stereo molecules. In thermal condition, the compound will be formed as cis 5,6 dimethyl 1,3 cyclohexadiene will be formed. So this is the structure of this compound. Another round is 2E and 4Z 6Z octatriene, and the thermal reactions of trans 5,6 dimethyl 1,3 cyclohexadiene will be formed. Then it is a octatetraene, and then in photochemical reaction the same is here is a trans compound is 5,6 dimethyl 1,3 dichlorohexane will be found, and the same compound is 2E and 4Z6 octatetraene is in photochemical reactions the cis 5,6 dimethyl 1,3 cyclohexadiene will be formed, right? Then another one is formation of the same 2E and 4EZ and 5E disrotatory ring closures. The same structure will be formed. So here the table is Woodward-Hoffmann rules for the electrocyclic reactions. Number of conjugated by bonds, even number and odd number. Here talking about and the reaction condition. Even number is the thermal and photochemical. The conrotatory will be allowed mode and ring closures. And photochemical reactions disrotatory allowed mode for the ring closures. In case of the number of the conjugated bi bond is odd number, the thermal photochemical reactions is the disrotatory and conrotatory. It is just like that opposite, right? Thermal and photochemical reaction, right? So PMO methods, the Huckel rule of aromaticity, the monocyclic planar conjugated system with 4n plus 2 by electrons is aromatic and consequently the tabling of the ground state. The system with the foreign by electrons is unstable and it is referred to as anti-aromatic system. And however, the further the calculation shows that these rules are reversed by the presence of the nodes in the array of atomic orbitals. So system with 4n plus 2 by electrons and a node is anti-aromatic while system with is 4n by electrons and node of is aromatic, right? The applications of these rules to pericyclic reactions led to the generalization that thermal reactions takes place into via aromatic transition state. And then photochemical reaction proceeding through the anti-aromatic transition state TS, and cyclic TS is said to be an aromatic and isoconjugated with the corresponding aromatic system. If the number of pi electrons involving the conjugated atoms are the same as in the corresponding aromatic system, we have only to consider cycloarray of atomic orbital representing those who orbitals which is undergoes to change in the transition state and assigned to sign to have the functions of the better manner to overlap. Number of pi electrons and number of the nodes is array of conducted, right? So this is the PM methods. Here is image will show the some different color of blue and red. Here A and B. So here the con-rotatory and electrolytics is ring closer and opening 4 electrons. Here is formed as a node. Here it is closed like this. And then same is disrotatory electrolytic and ring closer opening of 6 electron. Here the 4 electron, here the 6 electron. Its no node will be formed, right? Then is cycloadditions of reaction. Next we are going to cycloadditions of reactions involve the formation of the cyclic product due to the additions of the two different bi bonds containing the components which are jointly by the newly formation of two bi bonds at their ends of the expense of two bi bonds. It is usually reversible and backward reactions also referred to as retrocycloadditions or cycloreversion. So this is for the cycloaddition reactions. Cycloaddition reactions involve the reactions of two components to form a cyclic compound and ring forming of reactions. Pericyclic type of both component of bi system, intramolecular and intramolecular reversion. The classification based on the number of bi electrons involved in the each component. The number are written within the square bracket of 2 bi plus 2 bi and 2 bi plus 4 bi etc. So this is for the A 2 plus 2 cycloaddition reactions. Here the structure is formed 2 plus 2 thermal condition, the no reaction. In otherwise the photochemical reactions will form like this. Okay, then stereochemistry of the cycloaddition reaction. Suprafacial and anterofacial approaches to the bi bonds. Here is the C, here the suprafacial approach syn addition, and it is just like the opposite anterofacial approach is anti-addition. So it is necessary to specify with respect to each bi component whether the approach is suprafacial or anterofacial formation. The cycloadditions of the ethylene to form of cyclobutane is 2 pi s plus 2 by s process. The thermal of Diels order reactions of 4 by s plus 2 by s process, right? So this is symmetry process of interaction of ethylene by orbital and cyclobutane sigma orbital. Here like this the blue color of nodes and red color, the SS and SA and AS and AA, and then also SS and AS and SS, SA and AA. So this is for the cyclobutane sigma orbital formation. So correlation diagram for the cycloaddition and the cyclo-reverse of the ethylene cyclobutane system. Cyclobutane system. So this is for the ring closes. SS and AS and SA and AA, and oppositely the SS and SA and AS and AA. So this is for the cyclobutane system of cyclo-reversion of the ethylene reactions when the photochemical or thermal reaction. Correlation diagram of 4s and for 2s cycloadditions of Diels order reactions. Here the same bond is bi bond. In the 4s and 2s methods, here like this bond is SAA and ASS. This is like this, and the energy, and for this SSA and for this formation SAS, it's just like that, is changing of this final product, right? And then frontier molecular orbital of the both reactants must be considered of the HOMO and LUMO position. Here the superficial bond formation, the color change, just like that you see, here is connectivity and here is connectivity, and then the antiofficial molecule is like that, is changing of these reactions of like this, right? Frontier molecular orbital analysis of the 2s plus 2s cycloaddition reactions. The HOMO position, it is blue is here and here, and blue, red green is opposites, right? And the LUMO, and the same is the ground state of HOMO is like this, and HOMO is like this, green and blue, it's opposite to LUMO, and its excited state molecule is opposite to, and also is opposite of LUMO molecules. So this is for the thermal condition of reaction, this is for the photochemical reaction, photochemical condition of the reactions. So totally it changed for the thermal and photochemical reactions. And frontier orbital molecule of the 4 plus 2 cycloaddition reaction, you see the dienes and dienophile LUMO, so overlapping of orbital have the same color or in same phase. So this is for the HOMO, dienophile and diene LUMOPhiles, right? Here it's a HOMO LUMO interaction of the 4 by S and 2 by S cycloadditions. So this is for the 4s and 2s thermally allowed reactions, LUMO-ethylene and HOMO-butadiene, and also is a HOMO-ethylene and LUMO-butadiene. It is anti-binding and is it's a photochemical reactions are forbidden. 4 by S and 2 by S, right? So for the 4 by S and 2 by S is thermally allowed but photochemically forbidden. So this is for the Woodward-Hoffmann rules for cycloaddition reactions. Some of the bonds, sigma bond, interact with the system of both reactant, even number, odd number. When it is a even number, the thermal reaction is antifacial and the photochemical reaction superficial, allowed modes for ring closures. In the same bi-bonds of reactions is odd number, thermal is superficial and photochemical reaction antifacial. So this antifacial ring closure system allowed to can occur only for the large ring. So another one is sigmatrophic reactions. One other example for the Cope rearrangement. Here is a ring opening for when the thermal reactions, it's opposite reaction, and Gleason reaction is here is like you see like this, right? Then 1,5 hydrogen shift reaction. Here 1,5 hydrogen shift reaction like this. It's a ring is charge is delocalized by electron is changing here thermal reactions. The compound will be formed like this, and then the same compound is, it is a hydrogen shift will be formed, it's a thermal reactions. Consider the transaction states reactions, the superficial reaction, the migration origin, the migration terms. So the antiofficial reaction also is like this, see like this. The sigmatrophic reaction have the cyclo transition state, and rearrangement must be the superficial. In the transition state has 6 or fewer atoms of the ring. So PMO methods of some examples for 1,3 shift and 1,3 is superficial reaction and antiofficial reactions. Then the reactions selection rule for sigmatrophic change of PMO method. 4 is number of nodes 0 to even. It is aromaticity, anti-aromaticity, and supra. Shift mode is supra H nu, and 4n is the odd, aromatic is antra. 4n plus 2 is 0 to even, add aromatic supra by, and 4n plus 2 rule odd, antra-aromatic, antra H nu, right? So so today we discuss about the pericyclic reactions. Thank you.